Points on a circle using sine and cosine. While it is convenient to describe the location of a point on a circle using an angle or a distance along the circle, relating this information to the x and y coordinates in the circle equation we explored in section 5.1 is an important application of trigonometry. A distress signal is sent from a sailboat during a storm, but the transmission is unclear and the rescue boat sitting at the marina cannot determine the sailboat's location. Using high-powered radar, they determine the distress signal is coming from a distance of 20 miles at an angle of 225 degrees from the marina. How many miles east and west and north and south of the rescue boat is the stranded sailboat? In a general sense, to investigate this, we begin by drawing a circle centered at the origin with radius r, and marking the point on the circle indicated by some angle theta. This point has coordinates x, y. If we drop a line segment vertically down from this point to the x-axis, we would form a right triangle inside of the circle. No matter which quadrant our angle theta puts us in, we can draw a triangle by dropping a perpendicular line segment to the x-axis, keeping in mind that the values of x and y may be positive or negative, depending on the quadrant. Additionally, if the angle theta puts us on an axis, we simply measure the radius as the x or y, with the other value being 0. Again, ensuring we have appropriate sides on the coordinates based on the quadrant. Triangles obtained from different radii will all be similar triangles, meaning corresponding sides scale proportionally, while the lengths of the sides may change as we saw in the last section. The ratios of the side lengths will always remain constant for any given angle. y1 divided by yr equals y2 divided by r2. x1 divided by r1 equals x2 divided by r2. To be able to refer to these ratios more easily, we will give them names. Since the ratios depend on the angle, we will write them as functions of the angle theta. Sine and cosine. For the point xy on a circle of a radius r at an angle of theta, we can define two important functions as the ratios of the sides of the corresponding triangle. The sine function, sine of theta, equals y divided by r. The cosine function, cosine of theta, equals x divided by r. In this chapter, we will explore these functions using both circles and right triangles. In the next chapter, we will take a closer look at the behavior and characteristics of the sine and cosine functions. Example 1. The point 3, 4 is on the circle of radius 5 at some angle theta. Find cosine of theta and sine of theta. Knowing the radius of a circle and coordinates of the point, we can evaluate the cosine and sine functions as the ratio of the sides. Cosine of theta equals x divided by r equals 3/5. Sine of theta equals y divided by r equals 4/5. There are a few cosine and sine values which we can determine fairly easily because the corresponding point on the circle falls on the x or y axis. Example 2. Find cosine of 90 degrees and sine of 90 degrees. On any circle, the terminal side of a 90-degree angle points straight up, so the coordinates of the corresponding point on the circle would be 0, r. Using our definitions of cosine and sine, cosine of 90 equals x divided by r equals 0 divided by r equals 0. Sine of 90 degrees equals y divided by r equals r divided by r equals 1. Notice that the definitions above can also be stated as coordinates of the point on a circle at a given angle. On a circle of radius r at an angle of theta, we can find the coordinates of the point xy at that angle using x equals r cosine of theta, y equals r sine of theta. On a unit circle, a circle with radius 1, x equals cosine of theta, and y equals sine of theta. Utilizing the basic equation for a circle centered at the origin, x squared plus y squared equals r squared, combined with the relationships above, we can establish a new identity. X squared plus y squared equals r squared. Substituting the relations above, r cosine of theta squared plus r sine of theta squared equals r squared. Simplifying, r squared multiplied by cosine of theta squared plus r squared multiplied by sine of theta squared equals r squared. Dividing by r squared, cosine of theta squared plus sine of theta squared equals 1. We're using shorthand notation. Cosine squared of theta plus sine squared of theta equals 1. Here, cosine squared of theta is commonly used shorthand notation for cosine of theta squared. Be aware that many calculators and computers do not understand this shorthand notation. In section 5.1, we related the Pythagorean theorem, a squared plus b squared equals c squared, to the basic equation of a circle, x squared plus y squared equals r squared, which we have now used to arrive at the Pythagorean identity. Pythagorean identity. A Pythagorean identity for any angle theta, cosine squared of theta plus sine squared of theta equals 1. One use of this identity is that it helps us to find a cosine value of an angle if we know the sine value of that angle or vice versa. However, since the equation will yield two possible values, we will need to utilize additional knowledge of the angle to help us find the desired value. Example 3. If sine of theta equals 3/7 and theta is in the second quadrant, find cosine of theta. Substituting the known value for sine into the Pythagorean identity, cosine squared of theta plus 3/7 squared equals 1. Cosine squared of theta plus 9 divided by 49 equals 1. Cosine squared of theta equals 40 divided by 49. Cosine of theta equals plus or minus the square root of 40 divided by 49 equals plus or minus the square root of 40 divided by 7 equals plus or minus 2 square root of 10 divided by 7. Since the angle is in the second quadrant, we know the x value of the point would be negative, so the cosine value should also be negative. Using this additional information, we can conclude that cosine of theta equals negative 2 square root of 10 divided by 7. Values for sine and cosine. At this point, you may have noticed that we haven't found any cosine or sine values from angles not on an axis. To do this, we will need to utilize our knowledge of triangles. First, consider a point on a circle at an angle of 45 degrees or pi divided by 4. At this angle, the x and y coordinates of the corresponding point on the circle will be equal because 45 degrees divides the first quadrant in half. Since the x and y values will be the same, the sine and cosine values will also be equal, utilizing the Pythagorean identity. Cosine squared of pi divided by 4 plus sine squared of pi divided by 4 equals 1. Since the sine and cosine are equal, we can substitute sine with cosine. Cosine square of pi divided by 4 plus cosine square of pi divided by 4 equals 1. Add like terms. 2 cosine squared of pi divided by 4 equals 1. Divide. Cosine squared of pi divided by 4 equals half. Cosine of pi 4 equals the square root of half. Remember, to rationalize the denominator, we multiply a term equivalent to 1 to get rid of the radical in the denominator. Cosine of pi divided by 4 equals square root of half multiplied by the square root of 2 divided by 2 equals the square root of 2 divided by 4 equals the square root of 2 over 2. Since the sine and cosine are equal, sine of pi divided by 4 equals square root of divided by 2 as well. The x and y coordinates for a point on a circle of radius 1 at an angle of 45 degrees are square root of 2 divided by 2, square root of 2 divided by 2. Example 4. Find the coordinates of a point on a circle of radius 6 at an angle of pi divided by 4. Using our new knowledge that sine of pi divided by 4 equals square root of 2 divided by 2, and cosine of pi divided by 4 equals square root of 2 divided by 2, along with our relationships that stated x equals r cosine of theta and y equals r sine of theta, we can find the coordinates of the point desired. X equals 6 cosine of pi divided by 4 equals 6 multiplied by the square root of 2 divided by 2 equals 3 multiplied by the square root of 2. Y equals 6 sine of pi divided by 4 equals 6 multiplied by square root of 2 divided by 2 equals 3 multiplied by square root of 2.